Well, this is the third of 4 videos on enols and enolates. And just as a quick review, in the first video we had the big picture wherein the alpha carbon, that is next to the carbonyl, was the key. We started there by taking protons, abstracting them, and putting them on this oxygen to make an enol. And we talked about the tautomerization then from ketones to enols, how ketones are favored, but an enol is more reactive and gives us a nucleophilic carbon that we can use for attack of Br and Br2 or Cl and Cl2, alpha halogenation. That's the first video. The second video, we looked at the same reaction but using the more aggressive enolate ion, this more reactive form of the enol, to attack Cl2 and Br2, and how we could use that same enolate ion to attack alkyl halides. So basically this was just a new nucleophile that we could bring into reaction with an alkyl halide. An old reaction, new nucleophile. In this third video what we're going to do is take a new nucleophile into an addition reaction with the ketones and aldehydes. So something we've seen before, acyl addition, that is reaction of nucleophiles with class 2 carbonyls. And we'll also look at a somewhat new reaction where we attack either a direct position of an alpha-beta unsaturated carbonyl, that is the carbonyl directly, or a conjugate position. We'll talk about that as our, second reaction. So we just have 2 reactions that we're going to talk about. The nucleophile that's new, this enolate ion, attacking class 2 carbonyls, acyl addition, and attack of the beta positions in an alpha-beta unsaturated ketone or aldehyde. So in the first reaction, what we're going to do, again, is just an old, in a sense, reaction when we're taking, this is the ketone or aldehyde, we're going to take a new nucleophile that we haven't seen before. This is just the enolate ion. We haven't seen or used this enolate ion specifically to attack a carbonyl and a ketone or an aldehyde, but we have seen this basic pattern of something attacking the carbon in a ketone or an aldehyde, advancing the electrons up to the oxygen and capping that with a proton to give us an acyl addition product. Because if you break this down, really all we have here is just the new nucleophile. It's big, it can be intimidating, but it's just really still a nucleophile connected to a carbon in that ketone or aldehyde, and the oxygen that took the negative charge becomes protonated. So it's really just an acyl addition product, an old reaction. Let's walk through that a little bit more slowly here as we go. So we said we need to have a new nucleophile. So we are going to use in base conditions, this is a strong base conditions, we're going to take off the alpha proton, leave a negative charge here, shown here, even though it's resonance delocalized to the oxygen. We're going to draw it with the negative on this carbon because this is the carbon that tends to favor favor attack of any particular electrophilic site, not this oxygen. So we're using this resonance, or this resonance form where the carbon is shown with negative to show our attack. We attack the carbon in the ketone or aldehyde to start our acyl addition reaction. We get the tetrahedral intermediate with the negative charge, where this is the tetrahedral carbon having the one alkyl group on the right. The other alkyl group here on the left has been moved up and out. And doesn't have to be any particular place. We just have to get ready to have 4 things bonded to this carbon that I've highlighted. The O here has to have a negative charge. And the carbon here no longer has a negative charge because the 2 electrons that were right here are now buried in a sigma bond. We've bonded the new nucleophile to the carbonyl carbon. And we've made the tetrahedral intermediate. This can now with the completion of the reaction, we can attack a proton in water. So these are usually going to come in some sort of, we need to have some sort of proton source. So we can attack a proton in the base, I guess, basic form of water. We can take a proton away, regenerate our catalytic base, regenerate it, and have our final product. This is called a beta hydroxyketone, or an aldol. Beta position to this carbonyl hydroxyketone, or we're going to just refer to it as our aldol. So aldols are formed by enolate ions attacking ketones and aldehydes. Now, one thing to point out, this is very important, it's still just an acyl addition reaction of a ketone with something as a nucleophile. So the old rules apply. If this is just a ketone aldehyde reacting with a nucleophile to give an addition product, only unbranched aldehydes favor the addition product, the aldol. Only unbranched, meaning, I guess starting back at this ketone, this is a ketone, so it can't even start off talking about it being an aldehyde. To be an unbranched aldehyde, we'd have to have a hydrogen here and just a linear chain of an alkyl group on the right side. So these products are generally not favored. It's going to, through equilibrium, favor the reagents. So this is a reversible reaction. With heating, more stable enones can form. So we'll look at that here after this next slide. Let's propose the aldols, again, that are less favored. In the case of unbranched aldehydes, we can favor the aldols. So in this case, we would have the rule apply because this is an unbranched aldehyde. You say, oh, how did you know that? Well, one, it is an aldehyde because we have a hydrogen off the carbonyl and an R group off the other side, and an unbranched aldehyde, just to give it another form, if we had butanol, 1, 2, 3, 4 carbons, this would be another form of an unbranched aldehyde, or we just have a simple straight chain alkyl group off the carbonyl. This would be another example of an unbranched aldehyde. So I've drawn the two of them here because what we're going to do is consider one of them to be the source of the enolate ion and the other one to be the electrophile that's attacked. So this catalytic amount of base, we know in strong base solutions and these ketones we have to go to the enolate. So I'm just going to, for purposes of the understanding of the reaction, take one of these to a enolate. So I'll take this one here and make an enolate. And there's not a lot of it. This is just a little bit of this form. This is not a reaction that favors the enolate. We favor the hydroxide. This is a little more stable, but this is basic enough to take a little bit of these protons away to make a little bit of the enolate ion, this carbon with a negative charge. That can then attack in the solution some unchanged enolate or unchanged aldehyde. We have just a little bit of it changed to this enolate. Advance the electron. We can take from ethanol or some product solution a proton and take it and protonate this oxygen. Regenerate, maybe not the exact same base, but at least something comparable. We could have ethoxide formed, and we get our aldol, which in this case would be favored in general because we have that unbranched aldehyde. We have a little bit more of this than we might expect given other ketones and aldehydes. This is, again, just addition product. We give it a special name. We've added to this carbon the nucleophile, the enolate, and protonated the oxygen in that carbonyl. We've given that thing this general name. This is called the aldol. Let's do it down here. Let's see if we can go quickly. We take one of these, react with the strong base, positive and negative. We take off one of the guess protons at the alpha position. You say, well, how'd you know to go to that carbon and not these others? Remember, we have to be next to the carbonyl. An enolate isn't just any carbon off the carbonyl negatively charged. It has to be the alpha position. So we took the proton away. There's just an itty-bitty amount of this formed. Itty-bitty, I guess. And that can attack the remaining amount of butanol. 1, 2, 3, 4, and this is an unbranched aldehyde, so we're going to favor this product. Let's draw that product. I'm going to go ahead and draw the nucleophile just down here. This is where the nucleophile is going to go. I've bumped the hydrogen up. The oxygen has a negative charge. Now this gets kind of hard. We have to say, okay, I'm connected through this carbon here. So I'm going to make sure to draw this carbon right here connected, and it has 2 more carbons off of it, a methylene and methyl group, has the carbonyl on the other side, and then we just of course cap with the proton, and we have, voila, our aldol. This takes some practice because these are just harder to draw. It's a pretty complex looking nucleophile. This one's going to get even harder. Now this is again favored because we have our conditions of with this acyl addition, where this is the nucleophile. Oops, the nucleophile. This is the carbonyl we attacked. This is the acyl addition product where the nucleophile has attacked that carbon and we capped with a proton. This acyl addition product is involving an unbranched aldehyde being attacked, so it's slightly favored in general. But this is not going to be. This is a branched aldehyde. So anytime, it doesn't matter what comes in as a nucleophile, and if I can spell this here, hyde, okay, aldehyde. These are branched aldehydes. This is a bigger group, so anything that comes in and attacks this carbon as a nucleophile to make an addition product, whether it be an enolate or something entirely different, it doesn't matter. The addition product's not going to be very favored. You're going to favor the reagents in the equilibrium. So let's go ahead and remember that. We've got our strong base, plus minus, strong base. We rip off, thankfully this has just 1 proton and we can rip it off. Make a little bitty, itty-bitty amount of this enolate that can attack the unchanged form of the aldehyde. And we'll do the same thing we did up here. Just draw H up top, and we're going to put the nucleophile down in this gap. Now it's going to get kind of hard because what we have here is a carbon that is in a 6-membered ring. So I'm going to go ahead and draw the 6-membered ring, and now it still has the carbonyl off of it. And that's our complex looking nucleophile. So I should have gone a little bit farther out here. That's just our nucleophile, our enolate, and we'll protonate in the ethanol solution. We have a source of a proton. We have the source of that from the ethanol we can make, and I know then this base would change from hydroxide to ethoxide, but at least this is protic, so we can give this oxygen that necessary proton to become neutral. And this is our, again, aldol that is not favored. We would favor reagents. This is an equilibrium reaction. All aldol addition reactions are equilibrium driven, so we have problems if the aldol is very unstable. You have to sort of either precipitate it out of solution. We have to, I guess, try to drive the reaction some way, excess reagent or whatever. All right, that's 2 examples, of the aldol addition reaction. Now let's take aldols that are formed in solution and try to drive them to more stable products. We can do that without changing any or adding anything new to the solution except for some heat. So we can say, hey, we can drive aldol formation, just NaOH and ethanol or NaOH and ethanol water. We can have these aldols formed. But if we add a little bit of heat to these solutions, we can push them a little further. So let's look at this reaction specifically up top here, the benzaldehyde, where we have a benzene ring connected to the carbonyl. Phenyl group is a benzene ring. This is non-enolizable aldehyde. This is an acetone, a ketone, which is enolizable. So we're going to start by taking that strong base hydroxide, and we can't attack a alpha proton here. There is none. There is no enolizable position here. We have no alpha proton. So we're going to take a proton from the acetone. So I'm going to go ahead and change this to CH2, have a negative charge. And in fact, it's less reactive, this ketone, than the aldehyde with the strong base, but there's just nothing to react in terms of the alpha proton and the aldehyde. So we go with the less reactive ketone and the strong base, the less reactive ketone and the strong base. If this would have been an enolizable aldehyde, we would favor enolate ion through the aldehyde, but it's just non-enolizable, and that's actually a good thing, because we can go back after we tear the proton off. This is more reactive carbonyl. So even though an itty-bitty amount of this enolate ion forms, it doesn't attack itself, acetone that's not deprotonated. It attacks the more reactive carbonyl in the aldehyde. So we have what's called a cross aldol reaction, a cross aldol reaction, where the ketone converted to the enolate ion, the itty-bitty amount, doesn't attack unchanged ketone that's floating around in solution. It attacks the more reactive aldehyde. So this is called a cross aldol addition reaction. So we'd attack cap with a proton. This is our nucleophile, the enolate ion that has added to the carbonyl and the benzaldehyde. So this is just our addition product, and this would be maybe not favored because we have some branching with the benzene ring, maybe less favored, maybe a little more favored. Benzaldehydes are pretty reactive, so this is our aldol. Now what we can do is say, okay, if that solution has a little bit of this floating around and maybe some reagent still left over because it's maybe 50-50, it's not driven all the way to aldol, we have some equilibrium between the reagents and the product. If we add heat, this high energy aldol can go to what's called an enone. This is called an ene for the sake of the carbon-carbon double bond you have there. And it doesn't matter if it's an aldehyde or a ketone, that carbonyl is kind of giving us the source of the name one, enone. So we have an enone that we can form. How do we do it? Well, we know that we don't change the basicity of the solution, whether it be a hydroxide or a ethoxide. We have the same amount of negatively charged strong bases floating around in solution. So we come back to that with this heat that's added, and we go after the same carbon that we went to make the aldol. So let's go find that carbon here. Well, if we box in our nucleophile, there it is. It's the carbon that was the negatively charged carbon that attacked in the benzaldehyde, this carbon here. So this is the key carbon, the alpha position. Go find it again and tear another proton off. If we tear another proton off of that position, we can make another enolate ion using that same carbon. We can make another negative charge there, and in this case what we're going to do is push off a bad leaving group. By having a full negative on this carbon, we can push off a bad leaving group, hydroxide. So we're still under base catalyzed conditions because we've regenerated the base that we used in the beginning of this process to go to enone to tear a proton off. We've regenerated another hydroxide. What we've made here is a ene or alkene, that has relieved some of this strain that makes any addition product unfavorable. The strain around this carbon that was in the aldehyde that we added the nucleophile to. So these addition products were strained in general because of the nucleophile having some steric hindrance with the OH group, phenyl group, and the hydrogen that sit off this tetrahedral carbon in the addition products. Doesn't matter what the nucleophile is. We said in general addition products aren't favored. But in this case of the aldol, we can drive off the OH group, relieve that strain. This carbon now is sp2, and we have a lower energy product that we can form called the enone. Get some conjugation going on here. The alkene here is conjugated to the carbonyl. That helps to stabilize the product. We can drive this reaction by removing that water that's formed when the OH attacks that same alpha position a second time. We can take that water away, and that helps drive the reaction. So those are some things we need to know about enone formation. They're driven by heat added to the solution wherein we make aldols. We can pull water away to drive the formation of the enone, and we get some conjugation that stabilizes this carbonyl. So that makes this carbonyl a little more stable than what we have in the starting reagents. And heck, if we can get the enone to drop out of solution as a solid, that's even better. Now let's take these enones, which are also called alpha-beta unsaturated ketones or aldehydes. They're also called by these names. Let's take those into reactions with different types of nucleophiles, whether it be weak bases, strong bases, or such. In this case, we have a strong acid that we could add an enone or an alpha-beta unsaturated aldehyde to. And we know the first thing to do with a strong acid is to protonate. What would we protonate? It would be this oxygen. So we know that we would protonate this oxygen. And if we did that, now we've jacked up the reactivity of the carbon here that shares this positive charge, so that the chloride, which is a weak base, could attack either this carbon here, this is called the direct position, or it could attack, because this positive charge by resonance is also expressed on this beta carbon. So we have two positions, the conjugate that we could attack and the direct position that we could attack. Now we need some rules now as to where we go with weak bases. Well, so we have those two sites defined. If we have enones or enones in the protonated form, the direct and conjugate positions. In general, strong bases bind to the carbon in the carbonyl, i.e. they go direct. Strong bases. And what we mean by strong bases, anything stronger than an O with a negative charge. So if we have carbanions, Grignard reagents, hydrides, naked hydrides I should say, like sodium hydride, they'll favor the direct position for attack. Weak and soft bases are going to go to the conjugate position. That is this position here. Well, this is certainly a weak base. So we're going to favor going to the conjugate position, and I'm going to draw our OH here. We have our chlorine that's now attached to this conjugate position. We move the pi bond to this gap as we pushed in with the chloride. And the pi bond went to a lone pair state on the oxygen, satisfying its positive charge and giving us a neutral oxygen. Now this is our addition product, but something's going to happen in this addition product, because I recognize that I have a functional group that by itself can transform or change, i.e. tautomerize. This is an enol. Just came out through the reaction. We see that we have an enol. So this is going to tautomerize to the keto form. How do we draw the keto form? Remember, if you have a doubt about it, just remember the resonance form. This is donating to this carbon here by resonance, partially negative. This is partially positive. So this proton, in the end, probably again through the solution, is going to end up here. So we're going to have our transfer of the proton to this alpha position of the enol. This is our keto tautomer that's favored. So this is our final product in this reaction. So don't forget, if it's a weak base, go conjugate. If it's a strong base, anything more basic than an alkoxide, O with a negative charge, they go to the direct position. They get kind of stuck when they attack the carbonyl and don't allow the carbonyl to reform. The conjugate positions, when they're attacked, give us a lower energy product because we get our carbonyl back. Carbonyl reformed. We always see that's what's driving the conjugate additions, is we get the carbonyl back. That helps to keep that lower energy than the direct addition product. Let me say though, however, this is a problem. It's a higher energy hill to climb because the partial positive charge here is not as significant as the partial positive charge here. So in general, it's a higher EA to a lower energy product. The direct position is easier to attack, and if it can't come off, it's sort of stuck there. So we'll look at some examples of how some get stuck. Sodium azide, this would be a weak base. We have a weak acid here. Acetic acid is just a carboxylic acid, and this is in water. So we may not be able to protonate this oxygen with a weak acid to start the reaction. We don't need to. We can, oops, that's the direct position. That's an option, but I have a enone here, so I need to hit the conjugate position. This is a weak base. Now I'm going to draw the enolate that we would form. This is a strong base. What we have right here, the enolate ion, is not a weak base. So we would have a problem if we didn't have some source of a proton in the solution that can satisfy this negative charge. It would just kick off the azide. It would come right back down and kick this off. But thankfully, we have a weak acid. So we can protonate using that weak acid, acetic acid. We get the enol, and of course this would tautomerize to the keto form, where we have this proton ending up where? Down here, and the carbonyl is reformed. So this is more favored, I guess, than the enol that we have. We know that the keto form is more favored. What are some other things that says, oh, it's more favorable than usual? This is a very large group, so this attack at the direct position would be even less favored in this case because the conjugate's more accessible. Electronically, less partially positive, but this is sterically more hindered. So there may be some even greater reasons why we go to the conjugate position. This is bulky. Again, don't stop at the enol that you form along the way. Go all the way to the keto form. That's the reason why the conjugate position is favored thermodynamically, is we get the carbonyl back. Other carbonyls can go through addition reactions. Carboxylates that are conjugated, we can do reactions with those. Amides that are alkylated esters. The carbonyl is less reactive in those cases because we have some donating groups. But for example here, if we had the amide, and I need to change this, let's make it alkylated. Let's go ahead and consider that type of direct attack we could have. Let's say we used, instead of a weak base, let's say we used methyl magnesium bromide. If we used methyl magnesium bromide, this would be a strong base, and it's a strong base where we have a basicity greater than that of an alkoxide. Well, the idea is here is if we attack direct, then what charge would the oxygen have if we attack direct? It would have a full negative. It would be a strong base, but it would be a weaker base than the methyl anion. Whenever we have that, a stronger base to a weaker base, we're going to favor the direct position. That's key. if this oxygen with negative is more stable than whatever your base was that's strong, then the direct position is favored. Alright, let's roll into a named reaction, and this will be it. It's called the Michael reaction. It's just given a special name because we're using an enolate ion that can form using the strong base to tear off a proton from a diketone, dialdehyde here, where we have a 1,3 relationship of carbonyls. Carbon in between, very acidic proton, can put a negative here. And an enolate ion attacking the conjugate position gives us a Michael reaction. Let me say that again. A Michael reaction is just a conjugate addition reaction wherein we use an enolate ion. So we're going to attack the conjugate position. We're going to have the proton, I guess, given from another 1,3 dialdehyde to that enol that's going to form. So we don't show it in the enol form, but this oxygen is going to be negative, it's going to be protonated, and then we're going to transfer a proton back to this position to get our final keto form. We have to have some acidic proton in solution to drive it all the way to the keto tautomer. But in the end, any addition reaction to the conjugate position, you basically just erase the pi bond, attach your nucleophile to this beta position, and of course you get the carbonyl back. This has to reform. So we advanced, has a negative charge here, but as that's protonated, it goes back to the keto tautomer, and we're done. This is just called, again, a Michael addition reaction, a Michael reaction, because the enolate's attacking the conjugate position. That's the Michael reaction, alkylation of the beta carbon using an enolate ion attacking the conjugate position. There are some other named reactions you may want to be familiar with. An enamine as a nucleophile attacking the beta carbon. That's a Stork reaction. If an enamine attacks this position, the beta position, the beta carbon or the conjugate position of an enone, we have a Stork reaction. Last one, we haven't really seen this much in our discussion of organometallic reagents, but if we have not a magnesium but a copper metal with alkyl groups off of it in the lithium dimethyl cuprate here, or called a Gilman reagent, this copper organic group bond, or this copper methyl group bond, is a little more covalent, so it's a softer base. It's not as reactive as a base from a Grignard reagent. It's got some weaker basicity to it. So we tend to, with Gilman reagents, go to the conjugate positions. If we had a Grignard reagent, like we showed here, we tend to go to the direct positions. So Gilman reagents, we take that organic group that's still sort of partially negative, bonded to copper, we take it to the conjugate position. And because copper can bind the negative charge that starts to form on this oxygen, we can maintain the conjugate addition product until we work up with water to remove the copper and reform the keto, or the carbonyl group. We can have a proton given to that oxygen that's going to give us an enol, and that'll tautomerize back to the ketone. So in the end, again, we just erase the pi bond if we have a conjugate addition, put the nucleophile on the carbon at the beta position, the pi bond being gone, and we are done. So I didn't go through the full mechanism here, but just remember, Gilmans go to conjugate positions. Grignards are considered hard, they go to direct positions. That's it. Bye-bye.